Great. Well, if I haven't met some of you, I'm Jennifer Holm. I'm very excited to be here. This is really great. So I'll be kind of talking on a little bit more of a focused topic on land surface processes, and then also trying to understand how tropical forests are responding to a changing climate. And even though this is a little bit more narrowly focused talk, I really hope this could foster some discussion later. So number one, why do we even care about tropical forests? Well, they do cover about half of the world's forests, and they cycle more carbon and water than any other biome, so they act as their own water pumps. And they do play a critical role in determining the Earth's energy balance. So with radiative cooling, and then they also mitigate climate change with storing a large amount of carbon. So I think kind of a new frontier with climate change modeling or climate modeling is really trying to put in the interaction of biogeochemical cycles into these climate models. Some of that's been brought up before, but I do think that is a major role of really capturing this interaction of biogeochemical cycles. And so with tropical forests really having a large carbon cycling component, it makes them a very critical area to study. So number two, we also want to know, how are tropical forests changing? There could be a long laundry list I could go down, from anywhere from land use, land cover changes, to increases in natural disturbances, to changes in hydraulic stress. But I think one of the major things is that these environments are going to be pushed into a new analog state that isn't seen on today's Earth. So they're already in the higher edge of the temperature range seen of environments on the planet, and they're going to be pushed into these new kind of novel systems. And there's also many things to tackle, to look at in the tropics, many different processes. So I think it's really important to kind of have this coordinated effort to really kind of address all these issues. So this is kind of a report that the DOE put out, just kind of showing, look, these systems are very critical and very important to study. So we all know that, tropical forests are important. They're important for the climate system. So what are the model predictions? We all know that, of course, the models are showing there's an increase in temperature over time. But then precipitation is a little bit more uncertain. But it looks like in the tropics there will be a drying effect, or a prolonging of the dry season. And then this has already been brought up, but I think it's really critical to see that the signal is still different with the land carbon uptake. So this is from Friedrichsen in 2006, where he showed that the land carbon uptake could either be a source or a sink. And then this is from their 2014 paper. So you see, we don't really have that much of improvement. There's still a large uncertainty in the ensemble of models of what is going to happen with the land carbon sink. And then also, to really improve these land surface processes and ESMs, we think it's really important to try to take this MODEX approach to try to improve modeling. So you first look at the uncertainties and the gaps in the model, and then you hope that will then inform these experiments. So the models are informing the experiments. And then it kind of goes back through this wheel where, after you run model-driven experiments, they go back and inform the models. So I think once you iterate through that a couple times, hopefully we could create these new cutting-edge models that, again, look at the frontiers of land use changes and different things with land surface processes. So I'm going to see how many times I can say frontiers in this presentation. But after this, I'm going to kind of focus on a couple specific projects that I've worked on in the tropics. So to try to understand how tropical forest systems are changing, but then also kind of learn a little bit of what we can improve on. So it might be getting kind of a little technical, but I'll just try to do a quick overview on some projects. So for a little bit of background, turnover rates are increasing in the Amazon. So we see from this Phillips et al. Paper, where it's 30 years of long-term inventory data, where it shows this increase in both mortality and recruitment. So this is sort of the million-dollar question, is trying to understand why these forests are naturally increasing in turnover and increasing in mortality. And with that, natural disturbances are also increasing. So there's large changes due to deforestation and land use change, increases in storms, and all this has large effects on the carbon storage and carbon cycling. So one of my studies is we'd really like to understand what will happen with these increased disturbance rates over time. So while in general turnover rates are increasing across the whole Amazon basin, there's also a gradient So in the western Amazon, there are faster turnover rates compared to the central Amazon. So there's kind of this different gradient going on across. And then with that, that also leads into different wood density values. So in the western Amazon, there's lower wood density compared to the central Amazon. And then this figure from also Baker et al., it's a little bit important for my next slide. And what he shows is that allometric equations, when you do not take into account wood density, then there's no difference in above ground biomass. But when you do take into account this gradient and this difference in wood density, then you get a significant drop in above ground biomass. And all this, again, is important because we want to know the amount of carbon stocks in these forests and how they're changing. So one of my questions is I just want to understand, well, what happens if we increase the disturbance rates in the central Amazon to match the western Amazon? And so I want to know if the variability in these forest dynamics and carbon stocks between these two regions, can that be explained by this variability in disturbance regime? Next. Yeah, so what I did is I have used two different models. I've used a dynamic vegetation gap model to look at the consequences of these increased disturbance rates. And then I also looked at, oh, no, not forward, I meant to use the red button. And I also looked at changes of disturbances in CLM. So Zelig-Trope has a stochastic mechanistic mortality algorithm where, if you guys know CLM, just has a constant annual mortality rate. So the point is we want to eventually try to improve Earth system models to try to capture this disturbance recovery process. So I think I kind of mentioned this. Basically what I did was just increase the disturbance in the central Amazon using both these two models. And kind of quickly what I found is that basically we think that disturbance might not be an indicator of the gradients across the Amazon. So instead, that this gradients of differences is probably due to other environmental factors or community composition. And that's kind of what all these figures are showing. They're a little busy, but the green is all empirical data, and the black is the models, looking at things like above ground biomass, wood density, growth rates. And basically, when you do the treatment of high disturbance, they all show a different effect of what you see in the field. So the models are getting this right answer, this drop in above ground biomass due to disturbance, but it's getting it for the wrong reason. And also I learned that CLM kind of does a poor job at capturing some of these tropical forest processes. So kind of moving on, I also really think that dynamic vegetation is very important to put in ESM. So trying to get this size class, this age class distribution, because all this is important for trying to understand changes to carbon, and then trying to understand how is this tropical forest carbon sink changing, and what are the uncertainties with this tropical forest carbon sink. So this is just a quick figure from Stevenson that came out this year, where he looked at a global analysis of all trees across the globe and showed that larger trees are increasing in growth rates. So the larger trees growing more. And that might not be true in the tropics. What we're finding is the opposite effect. In the tropics, it's actually these smaller stems that are increasing more in biomass increment, higher above ground biomass, higher stem density. And this is the ecosystem demography model that captures this. So when you have ecosystem demography, when you have this size class structure, you could get this. So one of our goals is trying to put the ecosystem demography model into CLM, and so we're starting to do that. So there will be CLM Ed. Okay, kind of jump into Puerto Rico now. It's sticking with using this dynamic vegetation tool. We wanted to try to evaluate the recovery from land use change. So we went to Puerto Rico, which has a very high land use history, and we wanted to understand how will these forests recover? How long does it take when well, basically these abandoned fields that have been really kind of degrading the soil, what is their recovery process? And we find that abandoned fields on these degraded soil conditions, they could take anywhere from 50 to 100 years to reach a mature status. So there's a little bit of a lag time. This figure might be a little bit hard to tell with all these things on it, but what I'm highlighting is that a secondary forest that's 100 years, that was on degraded soils, it's the same as a mature 50 years. So that's kind of like that 50-year to 100-year lag time. So we think this is important because I was talking about those new analog states, that these tropical systems are going to be pushed into new novel states that we're not going to see. And these dry tropical forests are an example of that. They're already in these very hot, very dry conditions. So this might be a good place to try to understand what will happen to these systems in the future. So it's still sticking in Puerto Rico, it also has a high hurricane frequency. It gets impacted by hurricanes a lot. So we wanted to also use modeling capabilities to try to understand what happens to carbon cycling dynamics with an increase in hurricanes. So this project, it didn't try to predict how hurricanes are changing in the future. There's still, the debate of whether it's more intensity or more frequency, but everybody's agreeing it's probably higher intensity storms. So we just did two scenarios where, what if storm intensity goes up, and then separately, what if storm frequency goes up? And we found that there was really kind of no significant effect, and this is above ground biomass, with an increase in storm intensity, but with higher storm frequency, you do get a decrease in biomass. And it's because these forests are actually more resistant to hurricanes, but when you start hitting them more and more and more, then they start losing their biomass, which is kind of an interesting result. Let's see. I think this is almost my last slide, kind of going all these different kind of overview topics. Another thing that we think is very, very important in the tropics is trying to model this biosphere-atmosphere interactions and with BVOC emissions. So right now, we'd like to try to improve our representation of BVOC emissions in this coupled ESM models. But there's still kind of a poor understanding of what even really controls BVOC emissions. And I love this figure because I'm trying to keep doing the red. I love this figure because it shows, this is the latitude on the bottom, and it just shows the huge amount of BVOCs that are coming from the tropics and how much it outweighs the anthropogenic VOCs from the northern latitudes. And there's all these interacting effects that are going on with the biosphere and the atmosphere. So when you get an increase in BVOC emissions, it can increase aerosols, that then increase CCN and increase clouds, increase diffuse light. That can then help increase forest productivity. That then cycles around to maybe more BVOC emissions. So there's so many interactions going on. There's even a lot that I left off here, but it's a very interesting dynamic thing that we'd like to really kind of help improve and understand in the tropics. So we just completed this study where we did a quick sensitivity analysis of the Megan model that's inside. Okay, I think this is like almost my last slide. Yeah, where we looked at a sensitivity analysis of Megan and CLM. And just quickly, what we found is we did a sensitivity analysis of all the parameters that can influence BVOC emissions. And what we found was that leaf temperature actually contributes the most uncertainty to BVOC emissions. So 60% of the uncertainty in isoprene emission was caused by the uncertainty in leaf temperature. And then in addition, this is comparing the CLM predictions of leaf temperature to observational leaf temperature across the 4 seasons. And we see that CLM also isn't kind of capturing this upper bound. So it's missing this upper 10 to 14 degrees of leaf temperature. So there's all these kind of things that we could help improve on to just kind of help our modeling capacities. So yeah, so I think this is kind of a quick summary. I know a lot of these talks are a little kind of doomsday, kind of looking at sad scenarios, but hopefully we could all kind of learn and help just improve our modeling capabilities. And there are many, many interactions, of course, that are critical to the Earth system and climate in tropical forests. So kind of like I mentioned, turnover is increasing in the Amazon, so mortality is increasing. And then also with that, disturbance is also increasing, so it's affecting this carbon storage. But we found that there's a lot going on with this gradient kind of across the Amazon, and that the disturbance regime might not really kind of be the driving factor of this differences in the Amazon. It might be something else kind of more complex. And I really think, again, this dynamic vegetation is a very important tool that we really, really need to include. It's able to then capture these critical fluxes. And yeah, kind of these things that we looked at in the dry forest, that it might take them longer to recover from land use change, and maybe a hurricane frequency actually might have larger impacts on biomass. And yeah, and just kind of back to this MODEX approach again, I think it's kind of really important to maybe start using this circle a little bit more, where we do try to understand model uncertainty, try to understand biases, but then this can really drive model experiments too. And then model experiments go right back to informing this model. So there kind of needs this communication between observationalists and modelers as well. And again, this is kind of what I want to leave us on, is that these systems are potentially going to go into new analog states. So it's very critical to try to understand what's going to happen. So yeah, I think that's all.
Exactly 15 minutes.
Ah, yes, right on.
Older speakers.
I might have been talking too fast. Maybe that was. Gotcha all.
5 minutes for questions. Jerry.
So just kind of a clarification question. So in your field, like you consider yourself an ecological modeler or land surface modeler, or is there a difference between the two, or is land models kind of subsumed ecological models, or where does this kind of stand?
You know what? It's completely blurred. I sometimes find myself saying both. I'm like, I'm a land surface modeler. Oh, sorry. So his question, I guess, kind of quickly summarizing, is do you see yourself more as a land surface modeler or an ecological modeler? What are the differences? Do they blur? Are they still two separate fields? And I find myself going back and forth, saying both. I'm like, I'm a land surface modeler, I'm an ecosystem modeler, and I think they are still very, very different, because a land surface modeler is also everything of the biogeochemistry cycle. So soils, microbes, roots, to leaf temperature, to cellular things. It could be a lot, but then I also find myself being like, well, isn't an ecological modeler that too? So I don't know if this is a new changing thing, maybe at my younger career as scientist, but I see at least people maybe in my position sometimes blurring it a little bit. So I don't know. Yeah.
I think you're in danger of slipping into integrated assessment.
I know. Yeah. We're all integrated assessment. Yes. So there's a.
Yes. I did like this experiential-driven co-production
the Modex
approach, the Modex approach, very much. Can you tell me the global models? Only the model you showed for that was one with a global map on it. Mm-hmm. And if we were only interested in the forests as contributors to a global climate change, then I guess the global models are adequate to represent this effect. Are there any local questions that you would need different types of models for, and are they, and how can they be impacted and informed by the new types of LiDAR-based individual tree type of high-resolution data? Is that being used, and is that being even upscaled to the global models, or is there a distinction between the two?
No, I think it operates at different scales, and the Modex term is a DOE Modex term. It's not something I came up with at all. It's a very, very big Modex, or DOE. I think the Terrestrial Earth Systems group, the TES group, maybe came up with it, or BER. But yeah, they love using this Modex term, so it's not mine. But yes, I think it can also be at regional scales, at smaller scales, to look at very small, kind of fine processes, but then also can be extrapolated up to the more global. Because I did show a global map, so it could be both, but of course, global experiments are very hard. So it's almost more at the smaller level and then learn from there.
Okay, so Marty's and Gusson, then James.
Switch.
Well, the interaction of surfaces with climate models is mostly on what's the water vapor exchange, what's the drag coefficient of the trees, and what's the energy exchange. And the problem with that, as best I'm sure you know it, is that the scales of the model are much bigger, many multiple kilometers, tens of kilometers, and the scales of ecosystems are very
one tree.
One tree. It's like a cloud problem. You try to represent there in so many clouds with one humidity or something like that. And it may not be doable, and then every time we change the resolution of the climate model, we have to recalibrate the parameterizations. I just wonder whether you think this is even doable in any accurate way.
This is an amazing question, and I think kind of gets at the discussion we were having right before lunch of all these things with scales. So there's multi-scales, multi-physics going on, and yes, everything with the land-atmosphere interaction with the energy fluxes, latent heat, it's critical. I think we can get down to a very, very small, fine scale, and it's a little bit of what we're starting to do with these new models of making them more dynamic vegetation, bringing in cohorts, making them more individually tree-based. It's going to be challenging, but I think it is possible. So we're almost going from this kind of individual tree cohort scale up to the watershed, and it's going to take a lot of computational power, but I think where we're going with computational power, we can't have that be a drawback. I think we should just shoot for it and try. But I don't know. I love how this might be a really good discussion with our group, is this scale issue.
We're really out of time, but
Okay, sorry.
Short question.
On your observational approach, you only limited your comment to MODEX, which is really focused on field experiments, but there are now a significant amount of long-term, large-scale ecosystem observational data records that could be brought to bear with your model to see if indeed you can say something about the gradient you were speaking about, or even to some extent multi-decadal variability. And so the models have the ability to do that, so do the observation capabilities. Are you planning, or are there some ongoing activities?
Yeah, totally. And we're just, I don't know if you've heard of the new NG Tropics project that started, and that's taking advantage of a lot of these long-term experimental studies. So we do now have decadal long trends and very, very long trends. And so really starting to incorporate the observations with the models. So yeah.
So by the way, the comment, this is really important because Jerry's question, Marty's question goes to the heart of this, is that those two approaches fundamentally are different. You talk about different time scales. The sort of the reason for following up with this land surface interaction was to come to terms with interacting with the climate community. But for your succession planning and the state changes, you definitely need to go to the ecosystem. You cannot do it based on this short-term flux-oriented type.
I agree.